So suppose you're on a boat in the ocean and you're taking pictures of your scenery with your phone when you accidentally drop your phone into the water. As the phone sinks deeper into the water, what do you see? Do you lose sight of your phone the moment it enters the water? Can you see your phone forever as it sinks lower and lower away from you? Or is it something in between? Do you see your phone for a while, but it gets progressively harder and harder to see? Why do you see that? So when light of a specific wavelength passes through a solution, some of that light is going to get absorbed. How much light gets absorbed will depend upon three factors. The distance through the solution that the light has traveled. We call this distance the path length, and in Beer's law, we symbolize it with a B. Sometimes this is symbolized with an L to represent the length instead. Now, this is why you can't see your phone on the ocean floor. The path through the water is so long that virtually all of the light leaving your phone gets absorbed before making it into your eye. The next factor is the concentration of a solute that absorbs that particular wavelength of light. We symbolize that concentration with C. If you were boating on the crystal clear waters of the Caribbean when you dropped your phone, you might be able to see it for quite a while as it sinks. Whereas if you were boating near the delta of the Mississippi River where there's lots of sediment in the water, you may have lost sight of your phone within the first foot or two. And the last factor is the amount of light of that particular wavelength that gets absorbed by the solute. We call this value the molar absorptivity and symbolize it with epsilon. The molar absorptivity will vary with different solutes and with different wavelengths. And when we combine these, we get Beer's law. So the absorbance, symbolized here with an A, is equal to epsilon BC. Now note here that the absorbance is related to the percent transmittance of light, where the absorbance is minus log base 10 of the percent transmittance of the light. So if we have 10% of the light gets transmitted, that means we have a value here of 0.1. The log of 0.1 is -1, and then the negative sign gets rid of the negative, so we have a positive value. So we'd have an absorbance of 1. So an absorbance of 1 corresponds to only 10% of the light being transmitted, 90% of the light being absorbed. An absorbance of 2, 1% of the light is transmitted, 99% gets absorbed. And so it's a logarithmic scale. In this experiment, you're going to use the SpectraVis Plus. It's going to connect to the LabQuest using a port on the side of the SpectraVis Plus and the USB port on the LabQuest. Now, inside this spectrometer is an LED over on this side where this white icon is. You have the cuvette in the center. That's going to hold your sample. On the far side, with this white icon over here, with this white triangle, that's where the sensor is. And so that sensor is going to be collecting light. When we have the cuvette in place, light is going to pass through the cuvette. Some amount of it is going to be scattered off of the cuvette. And we need to know how much light is striking the detector when we don't have any of our sample in place, and then how much light strikes the sample with our sample in place. So we need to collect what's called a blank. So you're going to fill the cuvette with a solution that is as close to the sample as we can get it without actually having any of our analyte, the compound that we want to analyze, in the solution. Now, with that cuvette, there are two different types of sides. There are these scalloped edges and flat edges. The flat edges are where we want the light to go through. The scalloped edges are where we want to hold it. We do not want to hold on the flat sides. And your fingerprints will scatter or absorb some of the light. So you want to make sure that you take a Kim wipe and clean off those flat edges, those flat faces, before you put the cuvette into your spectrometer. Now you want those scalloped edges facing the green and the purple sides, because we want the flat faces where the white icons are. Now you also want to make sure that you always use the same cuvette every time. If you're changing between different cuvettes, you're potentially changing the amount of light that's making it through the cuvette versus the amount of light that is scattered or absorbed by the cuvette. You may also have scratches on the cuvette. If you have scratches on the cuvette, you don't want to use that cuvette see your instructor or your TA to get a new one, because obviously those scratches can absorb or reflect or scatter the light. Now, when you fill the cuvette, you want to fill it about 3/4 of the way up, because the light is passing through roughly in the center of the cuvette. It doesn't have to be all the way up to the top, but if you have it less than half full, you're going to be passing light through both your solution and the air above the solution. So make sure you have it filled about 3/4 full. Now in this experiment, you are going to collect two different types of data with the SpectraViz. You're first going to collect a full spectrum of what the absorbance looks like across multiple wavelengths. And then you're going to have to pick which wavelength is the best wavelength for you to collect data at. You want that to be the wavelength that you have the strongest response to, so the highest absorbance. However, there are a few caveats here. So if we plot the absorbance as a function of the wavelength, you'll see something that looks like this. I've just drawn a generic curve here where you have some points where you have less absorbance, some other points where you have higher absorbance. You may also see a region that looks something like this, where there's lots of these peaks in there. Those are noise. You'll typically see that when you get to an absorbance value above 2.0, because as we already talked about, once you hit an absorbance of 2, you've absorbed 99% of the light. And with our SpectraViz spectrometers, these are not super high-end devices. And when you've absorbed 99% of the light, that means there's not much left. There's only 1% of the light left. And so beyond that, it's just really, really difficult to measure any light that's remaining. And so do not pick a wavelength for which the absorbance value is over 2.0. Once the SpectraViz gets to about 2.2 or 2.3, you just get lots and lots of noise. So we don't want to include any values that are over that. So in this graph, we want to pick a value that is the maximum value under 2.0 and away from any of that noise. So I would pick a value that's at the top of this peak here. So what you can do is tap on the screen at that point, and over on the right side, the LabQuest will tell you what that wavelength is. Write that wavelength down, and as long as you don't touch anywhere else on the screen and move on with the rest of the procedure, that wavelength will be the same wavelength that you see later on. That will be the one wavelength that you're measuring at. Instead of measuring across the entire spectrum, you'll only measure the absorbance at one wavelength and record those values. So then you're going to make some standard solutions and record the absorbance values at that one wavelength that you've picked for each of those standard solutions. So if we have the concentration down here of our analyte, we should see something that looks like this, where at least within some region, the absorbance will be related to the concentration. It will be a linear function there. And that means that then, when we can come along later and with an unknown, record an absorbance value, and then track over and go down to find the concentration that that unknown has in it. So let's talk about safety. Copper sulfate is an irritant and is moderately toxic to humans, so you want to take some care with it.